Good afternoon and good evening to those of you in Europe, and maybe we'll catch a few of you in Australia. Welcome to session 11 of the ESIG 2020 Fall Technical Workshop. We're going into the home stretch here with the last two sessions being held this week. I'm Charlie Smith, the Executive Director of ESIG, and I'll provide a few brief opening remarks. As you know by now, our plans were derailed by the coronavirus, and the fall sessions are all being held online. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoiva-san of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would ask you to note that the webinar will be an hour long. We will have 3 individual presentations of approximately 12 minutes each, and we plan to hold the questions for a 15-minute Q&A session after the last speaker. As we are doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. We would ask you to use Slido for your questions, as you will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG10, ESIG10, as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG10 as the event code. Session 11 today deals with the topic of advances in system operation and market design for high VRE penetration. Looking at a future where most of our generation could come from renewable energy makes this a critically important topic. The session will be chaired by Aidan Tuohy of EPRI. Aidan serves as the Program Manager for Transmission Operations, Planning, and Bulk System VG-DER Integration at EPRI, and is the Chair of our System Operation and Market Design Working Group. Aidan is a frequent and active participant in our ESIG activities and a good friend of ESIG. Aidan, we appreciate having you here, and I'll now turn it over to you.
Thank you, Charlie. Appreciate the opportunity today to share this session. 3 very interesting presentations. As Charlie said, we'll have about 12 minutes each and time for Q&A at the end, so please do use the Slido information. We'll do the presentations in the order on the screen here, so we'll start with Jim. As Jim's presentation is coming up here, Jim's a senior engineer with the Power Systems Engineering Centre at NREL. She's researched including stability, large renewable integration, and multi-timescale dynamic modeling. She's the editor of International Transactions and Electrical Energy Systems and received the President's Award at NREL in 2018 and 2020. So with that, I'll hand it off to Jim, and please do put any questions in the Slido if you have them. Thanks, Jim. Jim, we're not hearing you if you're online, Jim. Jim, we're still not hearing if you can connect to the audio and video as well.
Aidan, I wonder if we should go ahead with Josh.
Yes.
Wait for Jim to get reconnected.
Let's do that. Josh, those of you who've been at NREL or at ESIG would know Josh, research engineer at NREL. He conducts research on renewable generation systems, looking at different infrastructure for possible future power systems. He's a master's degree from the University of Michigan. So, Josh, we'll hand it off to you.
Great. Thanks, Aidan. Thanks, everyone. It's a pleasure to be speaking with you again today. I'm going to give a kind of final update on this extreme weather events project that NREL, along with Justin Sharp from Sharply Focus, have been working on for the last year and a half or so. Some of you may recognize this project from the last couple of ESIG meetings, both forecasting workshops and the technical workshops. We've been using this forum as an avenue to present this work and get ongoing technical review and peer review from this community. That said, what I'm going to present today has received limited amounts of outside review from outside of NREL. So please don't distribute, quote, or cite anything you're going to see today. We're submitting the draft article to reviewers next week, so hopefully we'll get this out and published soon. But I do appreciate any comments or questions you may have, so please, I welcome those. So just to review what our objectives and motivations are here, we wanted to look at weather events that might stress the system today, and then other weather events that might stress the system in a higher variable generation future, just to understand how these different types of weather events might evolve as we increase our penetration of wind and solar. So we wanted to do a meteorological analysis of those events along with an assessment of variable generation resources. In addition, we're going to we've taken a subset of those events and gone ahead and done some production cost modeling to understand how commitment and dispatch of the system changes and evolves as our penetration of wind and solar increases during these particular weather events. For that production cost modeling, we've set up 3 different infrastructure scenarios to investigate these events. There's essentially events that represent 2024, 2036, and 2050 with the installed capacities in the upper right there. They represent about a 17%, 50%, and 65% variable generation annual energy penetration, at least according to the NREL READS model. Here's a summary of all of the events we identified. We've categorized them into newsworthy, or events that cause system stress today, even without super high penetrations of wind and solar. And then we have another set called challenges to planning, ones that we've identified via net load or other meteorological attributes of these events that we think might cause issues in a high variable generation future. In the report that we'll publish soon, we have case studies of each of these events that will be in the appendix, along with a summary of the production cost modeling of the events that you see here. This is the subset of events that we investigated there, along with what type of production cost modeling run we did. And in the next few slides, I'm going to go through a few findings that include figures that look like this. There's a lot presented here, so I wanted to take a quick minute to talk through what we see here. On the left-hand side of the figure, we see time series plots. All of the solid time series lines are the actual generation or load profile during the event we're analyzing for the 2050 infrastructure year. So we've built out wind and solar. So the generation profile reflects the wind and solar built out for 2050. The dotted line, on the other hand, is the generation or load profile, the average generation or load profile for the time around the event, looking at all of the meteorological years that we have in our data set, which is 2007 through 2013. On the right-hand side, we have statistical distributions we have 2 different types of statistical distributions. A solid distribution, which looks at the time of year around the particular event and the average daily generation and load during that particular season. The dashed distribution in the background is a distribution of all average, all days in our data set, the average generation or load for those days. The red dashed line is the days of the event placed within that distribution, so we can see where they fall. So I'm going to jump into the key findings that we've gathered from all of this analysis of the case studies that we've investigated so far. I do apologize ahead of time. We're going to run through these relatively quickly, but I wanted to make sure that this whole community got a sense of the types of findings that we're looking here so that we can get some feedback if you so desire. So the first finding is that variable generation tends to be available during the newsworthy events that we studied. So again, these newsworthy events are weather events that would stress the system today, generally leading to higher loads than are typical. On the screen here, we're seeing two different events. The one on the left is our winter storms in December 2013 that came through. We're specifically looking at the Western Interconnection there. And then we also, on the right, have the cold wave from February 2011 that led to the highest load days in our data set for ERCOT. What we see here is that load is extremely high in both interconnections during these particular events, but net load has actually been mitigated some based on the fact that both wind and solar have average or above average generation for most of the days during the event. That said, there are exceptions that exist. If you look at the distributions, you can see that there's 2 days in both events that actually are in the high tails of the distributions of the net load. And so there are still periods during these events where the resource might be low and not helping as much during this event. However, they tend to be short-lived relative to what we see in other types of events, which is finding number 2, that we have a whole host of events where the resource is relatively low, but it tends to happen during relatively uninteresting weather patterns. So we've pulled 2 different events, which we call kind of more benign weather events. One is a mild cold wave in February 2008, and then on the left-hand screen, and we're looking at the Eastern Interconnection here. And on the right, we're looking at another mild cold wave, but this time in February 2010, focused on the Western Interconnection. In both cases, the load profile, so the profile in green, is kind of right about average. There's a little bit of elevated load at the beginning of the event in the Eastern Interconnection for the February 2008 event. But for the most part, it's not particularly challenging for today's system. But as we add more wind and solar, these 2 events have particularly low resource availability during these times, which push, in both cases, the net load distribution up into the upper tails. It pushes the net load into the upper tails of the net load distribution, suggesting that these might be more challenging events due to lack of resource from wind and solar. And these are also somewhat prolonged. If we look at the 2008 cold wave, we see the 21st, 22nd, and 23rd all having pretty low wind resource relative to normal for this time period. So speaking of cold waves, our third finding focuses on the fact that evolution of operations during cold waves seems to change the most out of all of these different types of weather events we considered. What we're looking at here are animations of the of the temperature on the left-hand side, and we can see the cold wave kind of coming down the Rocky Mountain Front Range and seeping into the Eastern Interconnection and Texas interconnections. Along with it, at the beginning of the cold wave came high wind resource. So that's the right-hand plot animation, the darker blue being higher wind resource availability. So right as that front comes through, we see a lot of wind, but as that front moves out, but the cold persists, we actually see some areas of the Eastern Interconnection and Texas having very low wind resource like we're seeing right now. So it really determines how concerning a cold wave will be for future operations is what does the wind do after the front moves through? As the cold stays, typically the wind will die down as that front moves through, but what's uncertain is how much it will die down. I'm comparing 2 different cold waves on the left and right here. No, these are not electoral college maps, but these are the wind resource relative to normal. So blue would be higher than normal and red would be lower than normal. So on the left-hand side is our extreme cold wave, record cold temperatures throughout the Eastern and Texas interconnections. And as that cold wave leaves on the 2nd and 3rd, we see that there's areas of low wind resource, but other areas where it's actually stayed quite high. In contrast, the February 2008 or mild cold wave, that front came through on the 18th and 19th of February 2008, which I'm not showing a map for those. But the following 4 days after the front has moved through sees the lowest wind resource in our entire data set for the next 4 days across if we're considering the Eastern Interconnection. So really needing to understand what type of cold wave is going to lead to less wind after the front moves through. Based on our 2007 and 2013 data set, it appears that milder cold waves will lead to that, and there's meteorological reasoning that that should be the case. But we also do need to consider a larger data set to feel certain about that. Sticking quickly with the cold waves, on the left-hand side, we're looking at system dispatch during those same two cold waves that we were just looking at, with the left-hand side being the 2011 extreme cold wave and the mild cold wave on the right-hand side. And we're looking at how the system operations changes from 2024, 2036, and 2050. And we can really see just how much wind is available as that initial front comes through in both events. But that the 2008 event, we see the wind die down significantly over the next few days, requiring gas, hydro, and hydro to fill in the gap, whereas the 2011 event wasn't needed as much. On the right-hand side, I'm showing a net interchange plot between MISO and its neighbors for the 2011 event. I just want to highlight here that, yes, while the Eastern Interconnection on aggregate has very high wind resource, as we saw before, some areas of the Eastern Interconnection are not seeing that. So you do have to rely on your transmission infrastructure to be able to take advantage of that high wind resource in the upper Midwest during that time. We can really see on February 2nd and February 3rd in the 2036 and 2050 scenarios how dramatic a swing in the interchange between MISO and PJM there is, as MISO goes from importing from PJM to exporting all of its excess wind as the PJM wind dies down. Also something we considered was icing and low temperature cutoffs of wind turbines. This is particularly of interest during cold waves. Also gas outages is something we considered here that are also of interest during cold waves. These impacts tend to be local, but they do have to be dealt with, and what we see fills the gaps is changes the net interchange and gas generation as well. I'm going to have to flip through the rest of the findings relatively quickly, but for heat waves, we also have a finding focused on that. We see operations change pretty significantly from 2024 to 2050, mostly based on our increased PV penetration. But heat waves themselves don't tend to impact the aggregate PV generation. What it really impacts is how much wind are you going to have in the evening, given that the profile itself is relatively well anti-correlated with the PV. So you do see periods of high load not being as concerning because actually wind is available, whereas there's other times where load isn't as high, but wind is not available, and so our net load is quite high during those cases. I'm going to do a big caveat here that we did not consider any wildfire events, which would definitely potentially impact the PV generation, in addition to other power system infrastructure. Our other events focus on a flexible infrastructure. It can enable planning for geographic diversity. So we've got some events focused on transmission utilization and ability to share resources. I can't go into too much detail of that one. And then finally, our last finding is focused on hydro, and that availability and flexibility can really mitigate the impacts of weather events. So we did some sensitivities around decreasing how flexible the hydro was during oversupply and undersupply events, leading to increases in costs, which we'll focus on more in the paper. So here's a kind of just a summary slide of all 6 of our findings, which we'll focus on in the paper. But in the interest of time, I'm going to move on and leave you with an image of Hurricane Harvey. And thank you very much for your time. And again, I encourage questions now or even later. Feel free to contact me if you have them.
Thanks, Josh. Appreciate that. Getting through a lot of information there in a short period of time. I'm sure people will be interested in seeing the report. We are going to move on to Jin for the purpose of time. There's 15 minutes at the end, hopefully, to go through some Q&A. Please do go to the eSig10 on slido.com and add some questions for Josh or Jin and Audun as they talk, and we can get to those. So I already introduced Jin Tan from NREL. Jin, do you want to come off mute and present your slides?
Sure. I'm ready. Sorry for the technical glitch just now. Hello, everyone. My name is Jin Tan. I'm from NREL. Today, I'm going to introduce you a very powerful tool called MIDAS and its use case for Maui grid. First, a brief introduction about our MIDAS project. Second, what is MIDAS? And after that, I will give you one example to show how we use MIDAS for studying the inertia issues for the MIDAS for the Maui grid. At last, some conclusion. MIDAS Solar is a 3-year, $4.5 billion project funded by the DOE Solar Energy Technology Office. So 2 years ago, we gathered 7 partners to discuss, hey, what are the challenges of operating a grid with high renewables, and what are the modeling and the simulation gaps for the future grid study. So there will be a long list of challenges like low inertia, stability, you name it. Then we realized that when we consider using the PV for active power service, because the PV headroom is not a free resource, so we need to consider the interaction between the economics of the service provision and the dynamic control for performance. So however, there is no existing simulation tool and model can bridge the gaps between the scheduling and the dynamics. So we propose a new framework called MIDAS to help us to understand it. The key purpose of this framework is to simulate the interactions between economics, reliability, and the stability of the grid. So here is a diagram of the MIDAS. So there are 3 engines in the framework: the scheduling engine, external thermodynamic simulation engine, and the electromagnetic transient simulation engine. The scheduling engine can simulate from the day ahead unit commitment to the minute level economic dispatch. It will pass the dispatch results to our external thermodynamic simulation block every 5 minutes. When the dynamic simulation finishes 5 minutes run, it will send back the real-time operating point back to the economic dispatch module for the next round of optimization. So this closed-loop simulation framework has 4 features. The first is can capture the second level of the solar and the load variation. Second is to seamlessly to simulate the whole dynamic process during each dispatch time interval. Some mid-long-term dynamic components have to be added to this model, like the AGC load type changer. And the third one is this tool is user-friendly. The input files are all with the standardized format. The most important highlight is the output. First, the model can give us to evaluate the dynamic and the economics simultaneously. So we propose this 2-dimension matrix. We call it the cost reliability graph. So the traditional commercial software only can give 1-dimension information, like the pixels. Maybe they can compare the production cost. But if we have some dynamic-related services, it's hard to tell us a quantified number about how much dynamic benefit the new technology or control can achieve. Second, this framework can give us a more delicacy analysis for the stability, which is beyond the traditional stability analysis. I won't talk too much about that, but here I just want to mention we use a machine learning method and the selected scenarios for the EMT simulation here. So this framework includes many aspects of the grid operation. Someone may think this is another code simulation tool, but most importantly, we found the thing is that when we're studying the grid with the extreme high renewable, we need to change the mindset. We need to revisit the power system operation problems, not only from the different time scales separately, but also consider it from a multi-time scale as a whole. So it needs the delicacy analysis. So due to the limited time today, I will just give you one example how we use it for the Maui grid to show this concept. And we will focus on the scheduling and the external dynamic part, this part. And I hope I can have the chance to share some stability analysis work next time. Okay, so as we know, so Hawaii has a very ambitious goal to achieve 100% renewable goal in 2045. So the Maui grid plan to install 2 large megawatt scaled HPP in 2022, and also additional 3 HPP hybrid PV power plant and 1 battery in 2023. So the capacity of the additional HPP are very significant. they might be able to supply the 100% load by just using wind, solar. The question here is, how should we operate their system with very low or zero inertia? There are a lot of potential solutions, but today we just talk about the inertia requirements. So I missed some questions here. So do we need the minimum inertia requirement in the scheduling stage, and how much inertia do we need? Is there any risk and disadvantage to use some fixed inertia method? So here we compare two strategies. One is the no inertia requirement, which represents the traditional way. We don't need to consider the inertia constraints because we have more than enough synchronous generators online. And the other one is with the fixed inertia requirement, which is a very straightforward method, and people is considering to use it now. And our goal here is try to understand what's the potential risk of this fixed inertia requirement. And our method is adopt this multi-timescale methods. The first time scale is from the hour to year, where we'll perform our 1 year scheduling simulation. This will provide us statistical data through year-long simulation and analysis. The second time scale is from seconds to milliseconds, where we do a contingency analysis to understand the effectiveness of this inertia requirement. The third time scale is from 24 hours to seconds. This is our integrated dynamic scheduling simulation part. This is help us to quantify the trade-off between the reliability and the cost. First, after we run the 1 year simulation for the Maui grid of the 2 HPP case, we just show one case here. So we can get the generation dispatch. Here we show 1 week dispatch as an example. So the gray area is the represents the thermal generation. So we can see that during the noon hour, the thermal can be pushed to 0 due to a lot of utility PV and DPV online. Then we take a look at, the whole year inertia. We can see that there are more than 10% of the low inertia cases in the whole year. If we don't include the minimum inertia requirement in this scheduling model. Next, we kind of look at the PV curtailment duration curve. So we can see that with the minimum inertia requirement, PV curtailment increased from 0.9% to 13.7%. This implies that even we have 2 large battery energy storage with this inertia requirement, more HPP has been installed, more PV could be curtailed. Last is the inertia, the generation cost. Obviously, the generation cost will be higher than the no inertia cases, because in order to maintain the minimum inertia, it will bring more costly synchronous generator back to grid and give up some free solar. This will make the renewable eventually hit the penetration ceilings. So in this case, we need to revisit the fixed inertia requirement solution. So is there any limitation to use the fixed inertia method? Another question is to move forward to the 100% renewable. Can we just directly trust the scheduling results? We guess probably not, but how bad it is. So that's why we apply the largest N-1 contingency for all the scenarios of the no inertia cases. So the left figure just show the inertia versus the raw curve rate of change of frequency. Right one is the inertia versus the frequency nadir. So first thing we notice that in the red area, there is no results, because if you recall, there are more than 10% no inertia cases there. So when we use the PSS to try to simulate the scenario, the dynamic simulation are diverged. So which means those cases may cause the instability. This only can be captured by the dynamic simulation, but not the scheduled model. So secondly, if we take a look at the cases with inertia is larger than 354, which is the threshold we calculated before, we see all the runoff is below the 3 hertz. It looks like the constraint works, right? But if we take a look at the right figure, so we can see that the 59 hertz is the first stage of the unfrequent load shedding in HECO. So we see that even the inertia is larger than 354, but it still can guarantee our frequency nadir above the 59. So some scenarios still fall into the red box here. That's because the inertia is a more important factor. Is a very important factor to affecting the frequency nadir, but you still need to consider some other factors like headroom of your resource and how fast the resource can respond. Another observation here is the gray area. So those cases with the less inertia, but the system still can achieve a good record under the frequency nadir. So this study tells us we still need the inertia requirement in the scheduling stage, but if we don't consider the grid forming inverter. However, how to choose the proper inertia requirement will be sophisticated. We could propose some adaptive method, but before we go that far, so another thing we would like to know is what's the cost to put an inertia requirement there and how much dynamic benefits it can achieve at the same time. To answer that question, we need to consider both economics and the dynamic performance simultaneously. Here's an example. So we run the MIDAS to simulate a cloudy day with high wind, high solar for 24 hours. Two cases are compared here. This figure just shows 24 hours simulated frequency of the Maui grid. And you can clearly see that the cloud movements have a huge impact on the frequency variation during the day-night time. Also, it's clearly, after we have the inertia requirements, it did help improve the dynamic performance a lot. So we can use some dynamic metrics to evaluate that. We can see the CPS score and the frequency deviation definitely has been improved. But if you take a look at the cost and the renewable curtailment, we can see the cost almost being doubled, and there are a lot of PV and wind curtailments. So this study not only show the trade-off between the economics and the reliability, it also can quantify them. The system operator can use it to choose a proper inertia method, so it can so that it can help maintain the frequency in an acceptable range. And meanwhile, the method needs to be more economical efficiency. All right, so this comes to our conclusion and the findings. I just want to repeat it very quickly. So definitely the scheduling model only kind of like is not sufficient enough. It could cause some instability issues. We need to do the contingency check. And meanwhile, if we only simply to implement some minimal inertia requirement fixing it will, if we don't consider to convert the signal generator to the signal condenser, that will easily to make kind of like becomes a bottleneck to further increase the renewable penetration level. And also for those inertia requirements, it looks like there is a need to do adaptive requirements. And also when we consider those things, we need to consider the trade-off between the economics and the dynamics. For a more higher conclusion here, we think that stakeholders should evaluate the economic benefit and the reliability impact simultaneously during the policymaker planning and operation study for the grid with really high renewable penetration. At last, I would like to thank my MIDAS team, and I would like to take any questions at the Q&A session. Thank you very much.
Thank you, Jane. So as Jane said, we'll take questions at the Q&A. Please do go to the e610 on slido.com, enter your questions or vote on those that are there. Please also put the presenter's name in the question so we know who it's targeted towards. So Audun is the third and final speaker here this afternoon. He's a principal energy system engineer at Argonne, co-appointment at MIT. He's researching on power systems, markets, renewable energy, storage, and he's an MSc and PhD from the Norwegian University of Science and Technology. So, with that, I'll turn it over to you.
Great, thank you, Aidan. Thank you, Charlie, for the invite to present in this session. So, this presentation, I'm going to give an overview on some work we are doing in the IEA Hydropower Annex 9, and the focus on that And next is to look at valuing hydropower services, and we are currently conducting an international review and survey of how flexibility is valued in current and future electricity markets from the perspective of hydropower. We are leading this report on the US side with Chris O'Reilly at Oak Ridge National Lab and Abhishek Somani at PNNL as co-leads on this report. But it's a very international project that you can see from the list of main contributors here. So the background is that there is obviously a large increase in variable renewables out there in most parts of the world, and there is this increasing need for flexibility to operate the power systems. And electricity markets are evolving to address these challenges in various ways. And there are a number of different flexibility solutions out there, and hydropower is one of them. And Josh actually illustrated that in one of his results, where he showed that flexible hydropower can have a big impact on the production costs. So what we are looking at is how this flexibility procured in current markets, and what's the status and outlook from a hydropower perspective. And we draw this analogy between hydropower and this Argonne knife here, thinking that you can use hydropower for a wide range of challenges and services in the power grid. So let's see here. We use, when we look at power system flexibility, we use the definition from the IEA, which they came up with a couple of years ago on splitting power systems operations into different timescales, from very short-term issues around stability through medium-term, more like scheduling and dispatch decisions, to longer-term seasonal issues, as well as investment planning. So we wanted to find out how flexibility is procured across these different timescales. So we went out, we have conducted a survey where we asked for inputs, and you can see the sort of table of questions here organized by different timescales, and the questions were around what types of flexibility products are there, what types of procurement mechanisms, are these services compensated, to what extent does hydropower contribute, what's the size of these different markets, and also what are future developments. So we were happy to receive responses from as much as 14 different countries and regions around the world. And I'll show you a few of the results that we are compiling in the current report that we are finalizing. This shows the 14 different countries or regions, and as you can see, it's a variety of, in terms of how much renewables they have in the system. Some of these countries, like Norway, Canada, Brazil, they have the majority of their generation from hydropower. Others, like Germany, has a small share of hydropower, but a relatively large share of variable renewables, wind and solar. Let's see here. So the first question was around flexibility products. So these are the types of products that exist out there in various systems. And as you can see at the different time scales, there are typically multiple products that fit in that category, and also some of the services, like frequency-related services, they tend to occur across multiple time scales. And we asked about procurement mechanisms. We categorized those into interconnection agreements, bilateral contracts, and market-based solutions. And if you look at the latter one, you can see here that market-based procurement is used definitely quite frequently, with the exceptions of the very short time scales, where only about 20-25% of the respondents said that they use this mechanism to procure flexibility services. Interconnection agreements make an impact across the border, and bilateral contracts are also used frequently to procure different types of services. When it comes to compensation, most of the respondents did say that some, at least, if not all of the services are being compensated for most of the time scale, although that was less the case again at the very shortest time scale, sub-seconds to seconds. Okay, so what about hydropower? And hydropower does definitely contribute here. So this is basically the responses we got, again, sorted across timescales, where you can see that the vast majority of respondents did say that hydropower does contribute to flexibility all the way from sub-seconds out to days, months, and months to years. So that's a brief overview of the survey results. In this report, we are also including some a bit deeper dives into issues in various countries. This is the list of those 7 case studies that we are including. And Switzerland, for instance, they look at how they coordinate short-term grid and flexibility services with neighboring countries in Europe. The Norwegian case study is around using the large resources of hydropower back in Norway for balancing wind and solar power in other parts of Europe. Canada's contribution is from Hydro-Quebec, which offers an interesting different perspective, since their operations is managed through a long-term contract with the government, basically. From the US side, we are focusing on California ISO, and we are discussing flexibility requirements and also new market initiatives, both for the long-term resource advocacy construct in California, as well as new products and developments in the short-term day-ahead and real-time markets. Brazil focuses on long-term resource advocacy. I'll say a little bit more about that later. And Australia are discussing the need for deep storage or long-term storage, which hydropower definitely can provide, but there isn't really a path to get there yet, according to the Australian perspective. Whereas Japan is focusing on storage hydropower as a means to integrate renewables in various parts of the Japanese system. So let me look a little bit at a couple of interesting examples here that emerge from these case studies. In the European context, an interesting development there is that the ENTSO-V, which is the organization for system operators in Europe, they have over the last 2 years introduced joint definition of grid services or flexibility services in the short term to deal with load frequency control. So you have this frequency containment reserves that kick in right after an event, followed by frequency restoration reserves and recent reserves. These joint definitions are being adopted by various countries across Europe. At the same time, they are putting in place trading platforms where systems, countries, markets can trade these products in between each other's, making for a cost-effective way of procuring these services in system operations. The other example I want to mention is from Brazil. In Brazil, they have gone through several phases of restructuring. In the early 2000s, 2001 to 2002, I think they had some major drought years, which exposed insufficient capacity to meet demand, so they have severe shortages. After that, they restructured the market and they introduced the various segments of the market. And we can focus on the blue box or circle on the left here, the regulated contracting market. That's where distribution companies, they serve typically smaller consumers, and they have to use public auctions to meet their expected demand through purchasing power agreements that are then auctioned off on a regular basis through these public auctions. There are other parts of the market design as well, but if you look at the outcome from these public auctions on the right-hand side here from 2008 to 2015, they saw investments of 65 gigawatts of new capacity, and almost half of that actually from hydropower. So that, that's one example that illustrates that long-term contracts procured competitively through public auctions could assist in enabling investments in this technology in the long run. Okay, so some observations from both survey and case studies is that there are obviously a number of different revisions going on out there in response to changing system conditions. New markets are being introduced, like in Norway, they are introducing a product for very fast frequency response. In California, they've introduced FlexiRAM products in the last few years. Again, it's in market-based procurement mechanisms, primarily in the mid-time scale here, less in the short time scale. They emphasize the importance of standardized products, so the definitions to enable efficient trading. And also from a hydro perspective, transmission becomes very important since it's a geographically constrained resource. So we need transmission to access where the need is for flexibility. And also there are challenges around the potential lack of consistent long-term signals for investments in flexible hydro and long-duration storage in some parts of the world, although the Brazilian examples offers an example where long-term contracts actually are being used to procure and obtain investments in hydropower and other resources. So to conclude, a wide range of solutions out there, and hydropower definitely plays an important role in providing flexibility across all the different timescales. And we do think that the value of hydropower doing that to the grid is going to increase as we see more variable renewables being built, as well as more traditional generation resources being retired. Of course, this could also have the impact of more stress on hydropower plants. So you need to, when you refurbish and invest in new facilities, you should invest in flexible solutions that are durable. Some of the important challenges that I mentioned in the short term, sometimes a lack of compensation for some services, and then in the long term, robust investment incentives. Finally, we do think that this type of international collaboration and cooperation is important. Many of the challenges out there are similar, solutions differ, and that's something we can learn from across countries. So we are, as I mentioned, about to finish up this report, so keep an eye out on the website here of the IEA Hydro Annex 9, where we will post this as soon as we are done. With that, this is the picture of how we have all been operating during the pandemic. This is a workshop we had back in June, so you see some of the people engaged in this activity. So thank you, and looking forward to questions and comments.
Thanks, Aidan. I appreciate all the speakers keeping to the time. So Jane and Josh, if you could put on your videos as well, if you're in a place to do that, we can kind of get to some of the Slido questions. I think Ryan's going to put them up on the screen, but as he's doing that, I'm going to just start asking the most popular ones and get through as many as we can to use the voting if there's ones you want to really have up and ask. Jane, there's quite a few actually around fast frequency response and virtual inertia, emulated inertia. Have you considered that in the study and how that could help reduce the inertia requirement?
Thanks, Aidan. So in our project, yes, we will consider those fast frequency response. But in the study I present here, we haven't considered fast frequency response from the inverter-based resources. After for example, our assumption changes when the PV and the storage provide a fast frequency response or virtual inertia, like some other people asked, it definitely could reduce can let the system survive under much less inertia conditions. This is one thing. We are going to continue to do this type of study under our project.
Okay, thanks, Jim. I think that's the top two questions there. Josh, and for your one, there's a few that kind of had a few thumbs up. I do want to go to one that may be more interesting around the interconnections topic. Have you guys been studying the value of combining interconnections?
Yeah, so certainly the interconnection seam study is going through final peer review right now, and you can go to the website to find some looks at specifically looking at that question. For this extreme events work, we did not, so there is some increase in the interconnection between the west-east and ERCOT, although it's quite small, and we did not investigate different transmission designs at this point, although that is something that we would like to do for future work to look at more infrastructure sensitivities like that.
Thanks, Josh. And everyone trying to get questions to everyone. So Audun, for you, the hydro resources that you're aware of and looked at across the world, what proportion have second or sub-second response capability?
That's a good question. I mean, we haven't really tried to categorize that or collect data in terms of percentages. And based on the survey responses, though, they, as I showed, the vast majority of respondents do say that hydropower can provide services at the shortest time scale. So based on that, I would think that the majority of hydro plants out there can do that.
Okay, thanks. Maybe go back to Josh again around the question that's up on screen there around snow. I think you kind of mentioned or maybe hit on some of the icing. I'm not sure if you mentioned snow as well.
Yeah, so that we did not consider snow yet. So the reason we were able to do icing is because there's been a little bit more research at the lab to take our numerical weather modeling and be able to identify periods where turbines would have to be turned on, or wind farms would have to be turned down to deal with icing or cold temperature cutoffs. We've been working on the snow soiling problem or considerations, but it's been a little bit trickier. So by the time we were actually doing the modeling runs, we weren't able to include that yet. But that's definitely another question that needs to be answered for those cold wave events. I think it's going to be a similar result that local impacts will cause local issues and maybe it'll exacerbate blade icing situations, but we did not consider that in this study.
Okay. Thanks, Josh. The next one, actually, I guess, it was originally for Josh, but Jim, you may also have thoughts about it in terms of your lab colleague, in terms of how it might change results. So around the synchronous generator dispatch, so are you making assumptions there, Josh, around a certain amount of minimum generation online?
So we assume a certain amount of spinning reserves that are required. It's not required that those are coming from synchronous generators, although in many cases they are, especially when you consider both up and down, especially during these events where there isn't any curtailment of wind and solar anyway. So that's our requirement for, we have a spin requirement, but it's not a specific minimum amount of synchronous generation.
I guess maybe I might ask Jin then as well to comment around the applicability of MIDAS to systems like what Josh is studying. I mean, it's obviously orders of magnitude larger system. Have you thought about how MIDAS would scale up?
So in the MIDAS, we also consider kind of like just the normal system security for those synchronous generators dispatch, like the transmission line constraints.
How about, could you apply something like MIDAS to the Eastern interconnection or one of the larger interconnections?
The scalability is definitely something we need to consider. So far, we have a reduced WAC system we can play with, but if we want to use it for the detailed WAC interconnection, we need to consider how much kind of like details this model can handle, because we need to continuously to simulate a lot of dynamics for continuously. So we will see.
Got it. Just a quick one, Jen, for you. The MIDAS tool, is that publicly available, or are plans to make it publicly available?
We plan to publicly release it after we finish all the testing. And this is the end of our second year. So we plan to do that maybe when it's approaching the end of the third year, we are going to release it.
Understood. One of the other questions I see that down along maybe relates to both Audun and Josh around the interannual hydro variability. And maybe Josh, you could start by talking about
Sure.
how you consider that, and Audun maybe thinking about, you know, what are people doing in market service and that to think about interannual variability.
Yeah, so for our project, we do consider the hydrological year that the event happened as kind of the base case scenario. So if the event happened in 2011, we assumed energy limits for the hydro generators that reflected the hydrology of 2011. We did also do a few sensitivities on wet and dry years, which for some sensitivity analysis, but I had to skip through pretty quickly. So that is in there, and there'll be a little bit more detail in the report about that.
Yeah, if I can add to that. So obviously, hydro is exposed to variability as well, and typically over longer time scales. So there are various ways of dealing with that from a more technical perspective. You know, by building larger reservoirs, you have a larger storage, so you can better deal with that variability as it comes. Also, if you operate in markets, you'll see or hydropower producers manage their resource capacity depending on the current reservoir levels and the outlook for future precipitation. So you know, you end up pricing your resources accordingly. But yeah, so reservoir capacity as well as transmission as well to neighboring systems, which may have a different resource mix, I think are important aspects of this challenge.
Makes sense. Josh, the one on extreme heat and drought, you know, you already mentioned that you haven't specifically looked at that, but have you plans to extend the analysis, or do you have any thoughts on how that might impact this type of analysis?
Yeah, definitely. We do plan to extend the analysis and kind of this more wildfire in tandem with an extreme heat event is kind of one of the key events that we know that we didn't get to. We looked a little bit for one in our data set, but we didn't find one that was all that interesting. You know, our resource data should capture the smoke's impact on PV resource availability. And so we just didn't find that for this for the years that we were looking at. But that's especially given how prevalent it's been over the last few years in particular, that's going to be probably priority number one for extended work.
Cool. Related question: Did you see anything like the high temperature, high load kind of conditions that happened during August that led to some of the load shedding in California there?
Yeah, so we certainly saw elevated loads. We saw pretty tight adequacy and tight systems during that time. It wasn't. It wasn't in tandem with with fire, so we didn't do any kind of like transmission derates during those times, other than what you would normally expect in the summer. But yeah, a couple of the heat waves look similar, but I would say what we saw this year was probably even more extreme than what we've studied in our project.
Sure. Jen, one of the questions around the frequency variations you showed in the model, have you looked at how that compares to the actual frequency variability in Maui right now?
Yes. So for that frequency variation, that's similar to the frequency, right? And how we model it, basically we got some solar variations data from Maui. That's from the measurement, and then we use it for our simulation and simulate those frequency variations. And we didn't get a chance to compare it to the measured frequency to see what's the errors there. But we have the confidence that we think it shouldn't be off too much. Since we try our best, for example, when we consider those solar variations, we consider those GIS information, and also we use the real measurement data for the solar irradiance and power. Yeah.
I think we're coming to the end of the hour here, so rather than push on, I'll start wrapping up. I'm sure the speakers will be happy to talk with folks offline, contact them, or contact Ryan and he can put you in touch with them. Do you want to wrap up the session? So I'd like to thank the panelists. Great presentations, great discussion, and thanks everyone for their questions and participation. Got a lot of good insight into some of the future issues around operations and market design, and hopefully it's been stimulating for folks. Do want to remind you that the final session will be held this week. It's going to round things out nicely. There's a look at status and prospects for renewables and energy storage technologies. It's on Thursday at 2 p.m. Eastern US time. You're all invited to attend. The further information is on the EPRI website. So thanks again for the participation. Stay safe, and we look forward to seeing you then.
Thanks, everyone. Thanks, Aidan.
Thank you, everyone.
Thank you.